26 light-years from Earth, a telescope just spotted something that should not exist: water vapor. On a planet where the surface melts metal, scientists are stunned because this rocky world, named GJ486b, orbits so close to its star that a year there lasts only 36 hours. The temperatures reach 800 degrees Fahrenheit. No atmosphere should survive. Yet, the James Webb Space Telescope detected water's signature in the infrared light filtering through this alien world. But here's the twist that has astronomers arguing: the water might not be on the planet at all. It could be hiding in cool spots on the star itself, a cosmic mirage that would shatter what appeared to be the first atmosphere ever found on a rocky planet beyond our solar system. If you're enjoying this journey through the cosmos, hit that like button and subscribe to join us as we explore the universe's greatest mysteries. We're about to dive into one of the most controversial discoveries in exoplanet science. Prepare yourselves. We begin. The signal appeared on screens at the Space Telescope Science Institute, like a whisper from another world. Scientists stared at the data streaming back from the James Webb Space Telescope. They had pointed humanity's most powerful eye at a rocky planet, 26 light-years away, expecting to find nothing. Instead, they found water vapor. The discovery sent shockwaves through the astronomical community because water vapor should not exist where they found it. This wasn't a gas giant like Jupiter, where finding water is common. This was a rocky super-Earth, and if the signal is real, it would mark the first time anyone has ever detected an atmosphere on a rocky planet outside our solar system. The telescope had been watching a world called GJ486b as it crossed in front of its star, twice. Each transit lasted about 1 hour, and during those precious minutes, starlight filtered through the upper layers of the planet. That light carried fingerprints, chemical signatures, and buried in those signatures was the unmistakable mark of water molecules absorbing specific wavelengths of infrared light. 3 separate teams analyzed the data using 3 different methods. All 3 reached the same conclusion: water vapor. But here's where the story takes a strange turn. The water might not be on the planet at all. Red dwarf stars, the type this planet orbits, are covered in dark spots, similar to sunspots on our Sunday. These star spots are cooler than the surrounding stellar surface, much cooler, cool enough that water vapor can exist there, floating in the star's atmosphere rather than the planet's. The researchers ran computer models comparing both scenarios. A planet with a water-rich atmosphere produced one signature. Star spots with water vapor produced another. The signatures were nearly identical. Sarah Moran, from the University of Arizona, who led the study, put it bluntly: "We see a signal, and it's almost certainly due to water. But we can't tell yet if that water is part of the planet's atmosphere, or if we're just seeing a water signature coming from the star." The uncertainty is maddening. For decades, scientists have hunted for atmospheres on rocky exoplanets. They've found them on gas giants. They've found them on hot Jupiters, but never on a world like this. Never on a planet that resembles Earth in composition, even if it resembles hell in temperature. The stakes couldn't be higher. If this planet has an atmosphere, it would prove that rocky worlds can hold onto their air, even in the harshest environments imaginable. And if a planet this close to its star, this scorched, this bombarded by radiation, can maintain an atmosphere, then what about the billions of cooler, calmer worlds orbiting in habitable zones across the galaxy? But first, we need to understand what kind of world could even survive in such a place. Imagine taking Earth and squeezing it until it weighs 3 times as much, while only growing 30% larger. That's GJ486b. The gravity on this world would crush you. Your weight would triple. Every step would feel like carrying 2 versions of yourself on your shoulders. This is what astronomers call a super-Earth, a rocky planet more massive than our home, but smaller than the ice giants Neptune and Uranus. Scientists confirmed its existence in 2021 after spotting the telltale dimming of its star as the planet passed in front. The planet sits in the constellation Virgo, that sprawling pattern of stars visible from Earth's northern hemisphere during spring months. But GJ 486b is nothing like the gentle maiden that constellation represents. This world is a furnace. Its surface temperature hovers around 800 degrees Fahrenheit, hot enough to melt lead and zinc, hot enough to turn solid rock into something that flows. The planet's density tells us it's made of iron and rock, similar to Earth's composition, but any resemblance to our world ends there. Scientists know the planet's size because of how much starlight it blocks during transits. They know its mass from measuring the gravitational wobble it creates in its star. Combining those two measurements reveals density, and density reveals composition. Rocky planets have high densities because metals and minerals pack tightly together. Gas giants have low densities because hydrogen and helium spread out. This planet's numbers scream rock and metal. The world completes one full orbit in just under 1.5 Earth days. Think about that for a moment. A year on this planet is shorter than a weekend on ours. The planet races around its star at blistering speed, locked in a tight embrace that brings it dangerously close to the stellar surface. That proximity is both its curse and its key to discovery. The curse: it gets roasted by intense radiation. The key: being so close makes it easier to study than distant worlds. When the planet transits, it blocks a larger percentage of the star's light than a more distant planet would. That makes the signal stronger, clearer, but there's something even stranger about this world. Something that fundamentally changes what it means to have a day and night. The planet doesn't rotate the way Earth does, spinning freely as it orbits. Instead, GJ 486b is almost certainly tidally locked. One hemisphere faces the star eternally, baking under constant radiation. The other hemisphere faces the void of space, frozen in perpetual darkness. The border between these two extremes, called the terminator, is where the real chaos happens. If an atmosphere exists, it would try to transport heat from the day side to the night side. Winds would howl at supersonic speeds across the terminator, but that's only if there's air to carry the heat. And that's the question everything hinges on. So why does this planet orbit so close to begin with? 26 light years. That number sounds vast until you understand what it really means. 1 light year equals about 6 trillion miles. The distance light travels in a full year, moving at 186,000 miles per second. Multiply that by 26, and you get the distance to GJ 486b. In cosmic terms, this planet practically lives in our backyard. Our Milky Way galaxy spans 100,000 light-years from edge to edge. This world exists in the tiniest sliver of space near our own solar system. To put it in perspective, imagine the Milky Way as the continental United States. Earth sits somewhere near Kansas City. GJ 486b would be less than 2 blocks away. The Andromeda Galaxy, our nearest major galactic neighbor, would be in another country entirely. The observable universe would span the entire planet Earth millions of times over. We exist in a neighborhood, and GJ 486b is our neighbor. The star it orbits, GJ 486, is what astronomers call an M dwarf or red dwarf star. These stars are the most common type in the universe, making up about 70% of all stars. They're small, cool, and dim compared to our Sunday. GJ 486 has only about 30% of the Sun's mass and shines with less than 2% of the Sun's luminosity. You could stare directly at this star from Earth's distance without damaging your eyes, though you'd need a telescope to see it at all. The star appears as a faint red point in Earth's sky, invisible without equipment. Because the star is so dim, a planet needs to orbit extremely close to receive enough warmth for liquid water. That sweet spot, called the habitable zone, sits much nearer to the star than Earth's orbit around the Sunday. GJ 486b orbits even closer than that habitable zone, which is why it's so scorchingly hot. But the closeness has an advantage for scientists. The nearer a planet is to its star, the more starlight filters through its atmosphere during transits. The stronger the signal, the easier the detection. Scientists chose this system specifically because of its proximity. When you're trying to detect something as subtle as an atmosphere on a distant rocky world, every advantage matters. Distance matters. Brightness matters. The size of the planet matters. GJ 486b checks multiple boxes. It's close enough to study with current technology. It's large enough to block a detectable amount of starlight, and it transits regularly, giving scientists multiple opportunities to observe. But being this close to a red dwarf star comes with terrible consequences. These stars might be cooler than the sun, but they're far more violent. Red dwarf stars are monsters disguised as weaklings. They burn dim and cool compared to stars like our sun, but they live violently. These stars unleash devastating flares, massive bursts of X-ray and ultraviolet radiation that blast any nearby planets. The flares can increase a star's brightness by 10 to 100 times in just minutes. Imagine if our sun suddenly got 100 times brighter. Earth's atmosphere would be stripped away, oceans would boil, life would end. That's the reality for planets orbiting red dwarfs. The violence gets worse when red dwarfs are young. During their first billion years, these stars throw stellar tantrums constantly. High-energy radiation bombards their planets day after day, year after year, millennium after millennium. Any atmosphere that forms gets torn away molecule by molecule. The ultraviolet light breaks apart water into hydrogen and oxygen. The hydrogen, being light, escapes into space. The oxygen either escapes or reacts with surface rock. Either way, the atmosphere vanishes. GJ 486 is billions of years old now, past its most violent youth, but the damage may already be done. Scientists estimate this star has spent eons bathing its planets in radiation. That's why finding an atmosphere on GJ 486b would be so shocking. The planet should be airless, stripped bare, a dead rock circling a dying ember, yet the telescope detected water vapor. Somehow, somewhere. Red dwarfs have another trick that makes them dangerous. They live forever. Well, not literally forever, but close enough that the difference doesn't matter. A star like our sun will burn for about 10 billion years total. Red dwarfs can burn for 10 trillion years. That's 1,000 times longer. The universe itself is only about 14 billion years old, which means no red dwarf has ever died of old age. Not one. They're all still in their youth or middle age, and they'll continue burning long after stars like our sun have exhausted their fuel and collapsed into white dwarfs. This longevity creates an interesting possibility. If rocky planets around red dwarfs can somehow keep or rebuild their atmospheres despite the radiation, they have trillions of years to develop life, trillions of years for evolution to work, trillions of years for civilizations to rise. That's why scientists care so much about whether GJ 486b has an atmosphere. It's not about this one planet. It's about the billions upon billions of rocky worlds orbiting red dwarfs throughout the galaxy. But before we can answer that question, we need to understand just how fast this planet moves through its strange orbit. A year on GJ 486b lasts 36 hours. That's all. While you sleep through 2 Earth nights, this planet completes an entire journey around its star. The planet tears through space at roughly 200,000 miles per hour, held in place by gravity's invisible grip. At that speed, you could travel from New York to Los Angeles in about 80 seconds. The planet orbits so close to its star that the distance between them is only about 2 million miles, roughly 1/50th of the distance between Earth and our Sunday. This breakneck orbit creates consequences that would seem bizarre to anyone standing on Earth. There are no seasons on this world, no slow progression from summer to winter, no months to mark the passage of time. If humans somehow survived there, which they absolutely could not, they would celebrate a birthday every 36 hours. A teenager would be 3,000 years old in Earth years. The concept of a year would become meaningless. The close orbit also means the star appears massive in the planet's sky. From the dayside surface, the red dwarf would loom about 15 times wider than our sun appears from Earth. It would cover a huge portion of the sky, a vast crimson disk burning silently above. The star's light would be dimmer than sunlight on Earth, more orange-red than yellow-white, but the sheer size would be overwhelming. Standing beneath it would feel like standing under a ceiling that's slowly crushing down on you, even though it's millions of miles away. Scientists can calculate the orbit precisely by measuring how often the planet transits its star. Every time GJ 486b passes in front of its star, as seen from Earth, the star dims slightly. That dimming follows a predictable pattern. It happens every 1.467 days, like clockwork. The mathematical precision tells us that the planet's orbit is stable. It's not spiraling inward toward destruction. It's not being flung outward into the void. It's locked into a gravitational dance that has likely continued for billions of years. But here's the truly unsettling part. The planet probably doesn't experience that 36-hour cycle at all, because while it races around its star every day and a half, the planet itself almost certainly doesn't rotate at all. One side always faces the star, the other side always faces away. This phenomenon, called tidal locking, changes everything about what it means to be a world, and that brings us to one of the strangest aspects of this already strange planet. Imagine a world where the sun never moves. It hangs frozen in one spot in the sky forever, never rising, never setting, just burning in the same location for eternity. That's the day side of GJ 486b. Now imagine standing on the opposite hemisphere, where the sun never appears at all. Total darkness, perpetual night, frozen void. That's the night side. Between these two extremes runs a narrow band called the terminator, where the star sits permanently on the horizon, casting eternal twilight across an alien landscape. Tidal locking happens when a planet orbits close enough to its star that gravity pulls differently on the near side versus the far side. Over millions of years, this gravitational gradient acts like a brake on the planet's rotation. The planet slows down more, and eventually stops rotating altogether relative to its star. The same side faces inward forever. Earth's moon is tidally locked to Earth, which is why we always see the same lunar face. GJ 486b is almost certainly locked to its star the same way. The day side temperature reaches 800 degrees Fahrenheit, but the night side could be hundreds of degrees colder, maybe even close to absolute zero, depending on whether an atmosphere exists to transport heat. If there's no air, the night side becomes a frozen wasteland, where even gases like carbon dioxide freeze solid. The terminator region, that narrow band between eternal day and eternal night, might be the only place with bearable temperatures. Not comfortable, just bearable. It would be a thin strip of permanent sunset or sunrise, depending on which direction you faced. But here's what makes this relevant to the water vapor mystery. If an atmosphere exists, it changes everything about tidal locking. Atmospheres move. Air flows from high pressure to low pressure. The day side, being heated constantly, would have rising air and lower pressure at the surface. The night side, being cold, would have sinking air and higher pressure. This difference would drive winds howling from night to day at supersonic speeds. Those winds would carry heat from the scorched hemisphere to the frozen one, moderating both extremes. Scientists can test for this effect by measuring the temperature on the day side. If the hottest spot is directly under the star, that suggests weak or non-existent winds and probably no atmosphere. But if the hottest spot is shifted downwind, that suggests an atmosphere is transporting heat. Future observations with the telescope might reveal which scenario is real. For now, we only have the water vapor signal, ambiguous and frustrating in its lack of clarity. The temperatures themselves tell another crucial part of this story. 800 degrees Fahrenheit. Let that number sink in. At 450 degrees, paper ignites. At 621 degrees, lead melts into liquid. At 786 degrees, zinc melts. This planet's surface exceeds all of those thresholds. If you could somehow stand there, which you absolutely could not, your body would combust instantly. The ground beneath your feet would glow dull red from its own heat. Any water that somehow reached the surface would flash into steam before it could even form a puddle. Scientists calculated this temperature using multiple methods. They measured how much light the star emits. They calculated how much of that light hits the planet based on orbital distance. They accounted for how much light the planet reflects versus absorbs. The numbers all point to a world that exists at the edge of what rock can withstand. Basalt, a common volcanic rock on Earth, starts to soften around 2000 degrees Fahrenheit. This planet isn't quite there, but it's well into the range where different minerals behave differently. Some rocks would be hard and brittle, others would be soft and almost plastic. For comparison, consider Venus, the hottest planet in our solar system. Venus has a surface temperature of about 870 degrees Fahrenheit, remarkably similar to JWST. But Venus maintains that heat with a crushing atmosphere of carbon dioxide 90 times denser than Earth's air. The greenhouse effect on Venus is so extreme that the planet's night side stays nearly as hot as its day side. JWST might have no atmosphere at all. If it's truly airless, the temperature difference between day and night could be extreme. The day side 800 degrees. The night side potentially minus 300 degrees. A temperature swing of more than 1000 degrees across the terminator. This heat creates an interesting problem for the water vapor hypothesis. If water exists in the planet's atmosphere, where did it come from? The planet is far too hot for liquid water on the surface. Any primordial water would have been lost billions of years ago, boiled away by the star's heat and radiation. For water vapor to exist now, it would need a continuous source. The only plausible source is volcanic activity, releasing steam from the planet's interior. Deep below the surface, pockets of water could exist as superheated liquid or steam, held in place by immense pressure. Volcanic eruptions would blast this steam into the atmosphere, temporarily replenishing it. But there's a problem with this volcanic scenario. The planet would need to be geologically active. It would need a hot interior with convecting rock and erupting volcanoes. Scientists don't yet know if JJ486b is active or dead inside. The answer depends on whether the planet still has enough internal heat to drive plate tectonics or volcanism. For a planet 3 times Earth's mass, staying warm inside for billions of years is plausible, but it's unconfirmed. And that brings us back to the central mystery. Is the water vapor on the planet or the star? Cool spots on a burning star. That's the competing explanation that keeps scientists up at night. Just like our sun develops sunspots, dark regions where magnetic fields suppress heat, red dwarf stars develop star spots too. But red dwarf star spots are different. They're cooler, much cooler. While sunspots on our sun drop from about 10,000 degrees to about 7,000 degrees, star spots on red dwarfs can be even more extreme. The star's surface might be 6,000 degrees, but a star spot could be 4,000 degrees or less. That temperature difference matters because of water. Water molecules break apart at high temperatures, splitting into hydrogen and oxygen. But at lower temperatures, water can exist as vapor. Our sun is too hot for water vapor in sunspots, but cooler red dwarf stars can harbor water in their star spots. Scientists have confirmed this through spectroscopy. Water vapor exists in the atmospheres of cool stars. It pools in the dark spots, and when a planet transits, passing in front of the star as seen from Earth, it might pass in front of a star spot. Here's where things get tricky. When the planet crosses a star spot during transit, the light filtering through the planet's potential atmosphere also carries the signature of the star spot. The two signals mix. The planet's atmospheric water vapor, if it exists, gets muddled with the star spot's water vapor. Separating them becomes nearly impossible with current techniques. The researchers ran computer models simulating both scenarios. One model placed water in the planet's atmosphere, the other placed water in star spots. Both models produced transmission spectra that matched the Webb telescope's observations almost equally well. The difference between the models only emerges at shorter wavelengths of light, below the range that the telescope's near-spec instrument observed. That's why scientists need additional observations with a different instrument called NIRISS, which can observe at those shorter wavelengths. NIRISS could potentially see the divergence between the two models. If the water signal strengthens at shorter wavelengths, it's probably from the star. If it weakens or disappears, it's probably from the planet. But those observations haven't been completed yet. The mystery remains unsolved. Adding to the confusion, red dwarf stars like GJ 486 are magnetically active. They're covered in star spots. Some cover 10% or more of the star's surface. When a planet the size of GJ 486b transits such a star, it's almost guaranteed to pass in front of at least one star spot during the hour-long transit. That contamination is unavoidable. Every transit measurement from a planet around a red dwarf carries this ambiguity. Scientists first recognized this star spot problem back in 2018 years, before the James Webb Space Telescope launched. Researchers at the University of Arizona predicted that red dwarf star spots could mimic atmospheric signals. They warned that distinguishing between planetary atmospheres and stellar contamination would be one of the greatest challenges in exoplanet science. That prediction came true with GJ 486b. The very first attempt to find an atmosphere on a rocky planet around a red dwarf hit this exact problem. But the telescope has tools that can cut through the ambiguity. Light tells stories. Every time a photon passes through a gas, certain wavelengths get absorbed, while others pass through unaffected. The pattern of absorption creates a unique fingerprint for each molecule. Water absorbs strongly at specific infrared wavelengths. Carbon dioxide absorbs at different wavelengths. Methane has its own signature. By spreading starlight into a rainbow spectrum and measuring which colors are missing, scientists can read the chemical composition of distant atmospheres without ever visiting them. This technique is called transmission spectroscopy, and it's revolutionizing our understanding of planets beyond our solar system. Here's how it works for GJ 486b. The planet orbits its star every 36 hours. Once per orbit, as seen from Earth, the planet passes directly in front of the star. During that transit, which lasts about 1 hour, a tiny fraction of the star's light passes through the thin shell of atmosphere around the planet before reaching Earth. If the planet has an atmosphere, that is, if the planet is airless, the light just grazes the rocky surface and continues on. But if there's air, the light interacts with it. Different molecules absorb different wavelengths. When light passes through water vapor, the water molecules vibrate and rotate in response to specific infrared wavelengths. Those wavelengths get absorbed, converted to heat. The remaining light continues toward Earth, but it's now missing those specific colors. The Webb telescope collects that light and splits it into a spectrum, a rainbow showing how much light arrives at each wavelength. Where water vapor absorbed light, there's a dip in the spectrum. Where nothing absorbed light, the spectrum stays flat. Scientists observed GJ486b during 2 separate transits to confirm the signal. The first transit showed the water absorption feature. The second transit showed it again. The consistency meant the signal was real, not just noise or instrument error. Each transit lasted about an hour, giving the telescope enough time to collect sufficient photons to create a detailed spectrum. The observations used the telescope's near-infrared spectrograph, or NIRSpec, which operates at wavelengths between about 0.6 and 5.3 microns. That's the infrared range, where water vapor has strong absorption features. The spectrum came back mostly flat, meaning the planet's atmosphere blocks about the same amount of light at most wavelengths. But at the shortest wavelengths NIRSpec can see, around 1 micron, there was a rise, a bump in the data. That bump matched the wavelength where water vapor absorbs light. The match wasn't perfect. The error bars, representing uncertainty in the measurements, overlapped between the atmospheric model and the starspot model. But the signal was there, tantalizing, frustrating in its ambiguity. 3 separate research teams analyzed the data independently using different statistical methods. All 3 reached the same conclusion. The most likely explanation for the bump is water vapor. But all 3 also acknowledged that starspots could explain it equally well. The data wasn't clean enough to differentiate. That's the curse of working at the edge of what's technologically possible. You find hints, suggestions, possibilities, not certainties. The fact that scientists observed twice tells you something important about their approach. Observing once is interesting. Observing twice is science. When the telescope first captured GJ486b crossing in front of its star, the researchers saw the water vapor signal and immediately knew they needed confirmation. Space observations are expensive. Each hour of telescope time is precious, competed for by hundreds of research teams worldwide, but the potential importance of finding an atmosphere on a rocky exoplanet justified a second observation. The team got approval and waited for the next transit opportunity. The planet transits every 1.4, 6, 7 days, so the next opportunity came quickly. The telescope locked onto the system again. 1 hour of observation. The same instrument, NIRSpec. The same wavelength range. The same analysis techniques. If the first observation was a fluke or instrument error, the second observation would show something different, but it didn't. The second transit showed the same water vapor signature, the same bump in the spectrum at short wavelengths. The consistency meant the signal was real. Something in that system produces a water vapor signature. The question remained whether that something is the planet or the star. Multiple observations also help average out noise. Every measurement has uncertainty. Photons arrive randomly. Instrument detectors have imperfections. Cosmic rays can hit the detector and create false signals. By observing multiple transits and averaging the results, scientists reduce these random errors. The true signal strengthens while the noise cancels out. That's why astronomers observe transits multiple times whenever possible. It's not about mistrust of the instruments. The star is covered in so many star spots that the planet always passes in front of at least one. Scientists can't tell which interpretation is correct without additional data. Each transit observation generates hundreds of gigabytes of raw data. That data flows from the telescope to the Space Telescope Science Institute in Baltimore, where it gets processed through calibration pipelines. Those pipelines correct for instrument effects, remove known sources of noise, and convert raw detector counts into calibrated spectra. The calibrated spectra then go to the science teams, who analyze them using sophisticated computer models. The entire process, from observation to publication, takes months of careful work. But here's what makes this case special. The analysis required developing new techniques. Nobody had ever tried to separate a planetary atmosphere signal from starspot contamination with this level of precision before. The researchers had to create new computer models simulating star spots, new statistical methods for comparing model fits, and new ways to estimate uncertainty. In a sense, studying GJ 486b isn't just about this one planet. It's about developing the tools to study thousands of similar planets in the future. The results they got were both encouraging and frustrating. Flat spectra are boring. That's what makes this one interesting. When the transmission spectrum came back from the analysis, most wavelengths showed almost no absorption. The planet blocked the same small percentage of starlight across most of the infrared range. A flat spectrum suggests an atmosphere with no strong absorbers, or no atmosphere at all, just bare rock blocking starlight, which produces a flat spectrum by default. Scientists hoped for dramatic absorption features, deep valleys in the spectrum showing unambiguous signs of atmospheric gases. They didn't get them. But then came the rise at short wavelengths. Between about 1 and 2 microns, the spectrum curved upward. The planet appeared to block slightly more light at those wavelengths. That's where water vapor has absorption features. The rise wasn't dramatic. The error bars were large. But it was there, reproducible across both transits and consistent with water vapor's spectroscopic fingerprint. This tiny bump in an otherwise boring spectrum became the center of an international scientific debate. Flat spectra can have multiple causes. An airless planet produces a flat spectrum because there are no gases to absorb light, but so does an atmosphere with thick clouds, because the clouds block everything equally across all wavelengths. And here's the frustrating part. Starspot contamination also produces a nearly flat spectrum in some scenarios. When the planet crosses a star spot, the effective temperature of the star changes slightly. That temperature change affects the spectrum in complex ways that can mimic or hide atmospheric features. Disentangling these effects requires detailed models of both the star and the planet. The researchers compared the observed spectrum to 2 competing models. The first model assumed the planet has a water-rich atmosphere. They simulated what transmission spectrum such an atmosphere would produce, accounting for temperature, pressure, and cloud cover. The second model assumed the planet is airless, but the star has water vapor in its star spots. They simulated what spectrum that scenario would produce, accounting for star spot temperatures and sizes. Both models fit the data almost equally well. The statistical difference between them was negligible. This near tie between competing explanations is actually common in cutting-edge science. When you're working at the limit of your instrument's capabilities, clear answers are rare. You get hints, suggestions, competing interpretations that all fit the data within the error bars. That's not a failure of science. It's the nature of exploration. The first observations of anything new are always ambiguous. Clarity comes later, with better instruments, or more observation time, or new analysis techniques. What makes the flat spectrum surprising isn't just its lack of features. It's what that implies about the planet's atmosphere if one exists. Most atmospheric models for hot, rocky planets predict absorption features from carbon dioxide, water vapor, or other gases. Seeing almost nothing suggests either a very thin atmosphere, an atmosphere with unexpected composition, or no atmosphere at all. None of those options are what scientists hope to find, but all of them are scientifically interesting. The 3 analysis methods they used tell their own story. Science works by replication. If 3 different teams analyze the same data using different methods and reach the same conclusion, that conclusion gains credibility. That's what happened with GJ 486b. 3 independent research groups took the transmission spectra from both transits and ran them through different analysis pipelines. The first group used a technique called cross-correlation, which mathematically compares the observed spectrum to theoretical templates for different molecules. The second group used Bayesian analysis, a statistical method that calculates probability distributions for different atmospheric compositions. The third group used a technique called retrieval modeling, which uses computer algorithms to search for the best fit atmospheric parameters. All three methods pointed to water vapor, not because the researchers expected it or wanted it, because the data, when analyzed rigorously, showed absorption features consistent with water's spectroscopic signature. The probability that all three methods would converge on the same molecule by chance is extremely low. Either water vapor exists somewhere in the system, or something else is mimicking water vapor's signature so perfectly that multiple sophisticated analysis techniques can't distinguish them. The latter scenario seems unlikely, but can't be ruled out. Cross-correlation works by creating templates for different molecules at various temperatures and pressures. The computer shifts and scales these templates to match the observed spectrum. When a template matches well, the cross-correlation score is high. When it matches poorly, the score is low. For GJ486b, water vapor templates produce the highest scores. Carbon dioxide, methane, ammonia, and other molecules produced lower scores. The technique isn't perfect. It can be fooled by noise or systematic errors, but it's robust when the signal is real. Bayesian analysis takes a different approach. Instead of matching templates, it calculates probability distributions. The method starts with prior assumptions about what gases might exist and what temperatures are plausible. It then updates those assumptions based on the data. The result is a probability distribution showing how likely each atmospheric composition is. For GJ486b, atmospheres containing water vapor had higher probabilities than atmospheres without it. But again, the error bars were large. The probability wasn't overwhelming, just suggestive. Retrieval modeling is the most computationally intensive method. The computer runs millions of atmospheric simulations, each with different combinations of temperature, pressure, composition, and cloud properties. It calculates what transmission spectrum each simulation would produce. It then compares those theoretical spectra to the actual observations and identifies which simulations fit best. For GJ486b, the best-fitting models included water vapor. Models without water vapor fit the data more poorly. The consistency across methods is encouraging, but scientists remain cautious. All three methods share the same limitation. They can't distinguish between water vapor in the planet's atmosphere and water vapor in stellar star spots without additional observations at different wavelengths. The methods can tell you water exists somewhere. They can't definitively tell you where. That's why the star spot hypothesis remains viable despite three independent analyses pointing to water. But star spots themselves are more complex than most people realize. Star spots aren't just dark patches on a star's surface. They're windows into magnetic chaos. Magnetic fields, generated by churning plasma in the star's interior, burst through the surface and suppress heat flow. The suppressed regions cool down and darken, creating spots that can be larger than entire planets. On our sun, sunspots come and go in an 11-year cycle, driven by the sun's magnetic field, flipping polarity. Red dwarf stars, like GJ486, have similar cycles, but their magnetic fields are stronger, and their star spots can cover a much larger fraction of the stellar surface. Some red dwarfs have star spots covering 10 to 20% of their total surface area. Imagine if the sun had spots that large. Earth would experience dramatic cooling as huge dark patches rotated across the solar disk. Our climate would swing wildly as the sun's output fluctuated by 10% or more. Life on Earth depends on the sun's relative stability. Rocky planets around red dwarfs don't have that luxury. They orbit stars whose brightness can change significantly over days or weeks. The temperature inside a star spot on a red dwarf can drop to about 4,000 degrees Fahrenheit or lower. The surrounding star surface might be 6,000 degrees. That 2,000 degree difference creates a boundary where molecules that can't exist on the hot surface suddenly become stable. Water vapor forms, carbon monoxide, titanium oxide. These molecules concentrate in star spots, creating chemical signatures that can be detected spectroscopically. When a planet transits, passing in front of the star, it can cross these molecular-rich regions. Here's the problem for atmospheric studies. When the planet passes in front of a star spot, the spectrum contains contributions from both the planet and the star. If the planet has a water-rich atmosphere and the star spot also has water vapor, the signals add together. If the planet has no atmosphere but crosses a water-rich star spot, the signal looks like a planetary atmosphere even though it's not. Separating these contributions requires observing at multiple wavelengths and comparing how the signal changes. Some wavelengths are sensitive to temperature, which differs between planets and stars. Other wavelengths are sensitive to pressure, which also differs. By combining observations across many wavelengths, scientists can theoretically separate stellar and planetary contributions. But JJ486b's observations didn't cover enough wavelengths to do this separation. The NIRSpec instrument observed from about 1 to 5 microns, an excellent range for detecting water vapor, but not enough spectral coverage to distinguish planetary from stellar sources. That's why additional observations with NIRS are critical. NIRS covers shorter wavelengths, down to about 0.6 microns, where the two scenarios diverge more dramatically. Star spots also rotate with the star. JJ486 rotates about once every few weeks, which means star spots move across the stellar disk on similar timescales. Between the two transit observations, months apart, any specific star spot would have rotated many times. If the water signal came from one particular star spot, the signal should have changed between observations as that spot rotated in and out of view. The fact that the signal remained consistent suggests either the water is in the planet's atmosphere, where it wouldn't change with stellar rotation, or the star is so covered in star spots that the planet always crosses similar amounts of water vapor, regardless of which spots it passes over. Understanding star spots isn't just academic. It's fundamental to interpreting observations of every planet around every red dwarf. Red dwarf stars are atmosphere killers. The same radiation that makes sunlight possible on Earth becomes a weapon around these angry suns. Ultraviolet light, invisible to human eyes, carries enough energy to break apart molecules. X-rays carry even more energy, ionizing atoms and stripping away electrons. When these high-energy photons hit a planetary atmosphere, they cause havoc. Water molecules split into hydrogen and oxygen. Oxygen combines with nitrogen to form nitrogen oxides. Hydrogen, being the lightest element, escapes to space. Over millions of years, entire atmospheres can be lost. Young red dwarfs are especially violent. During their first billion years, they undergo frequent stellar flares, massive explosions, releasing as much energy as 1 billion atomic bombs. These flares increase the star's X-ray and ultraviolet output by factors of 10 or 100 from minutes to hours. A planet orbiting close to such a star experiences atmospheric bombardment unlike anything Earth has ever seen. Even our sun's worst flares pale in comparison. The radiation doesn't just strip away gas, it can sterilize entire planetary surfaces, breaking down organic molecules and making the surface uninhabitable. Scientists estimate that Earth would lose its atmosphere in less than 100 million years if placed in JJ486b's orbit. The solar wind, a stream of charged particles flowing from the star, would blow away atmospheric gas like a cosmic vacuum cleaner. Earth's magnetic field protects us from our sun's solar wind by deflecting charged particles, but magnetic fields can only do so much. Around red dwarfs, the stellar wind is stronger and the planet is closer, magnifying the destructive effect. Only the largest planets, with the strongest magnetic fields, can resist. JJ486b probably doesn't have a strong magnetic field. Rocky planets generate magnetic fields through liquid iron cores that convect and generate electricity. Earth has this. Mars lost its magnetic field billions of years ago when its core cooled. Venus never developed a strong one. For a planet to maintain a magnetic field, it needs enough internal heat to keep metal, liquid, and flowing. The larger the planet, the longer it retains heat. JJ486b, being 3 times Earth's mass, might have a molten core and active magnetic field, or it might be geologically dead, its core frozen solid. Scientists don't know yet. Without a magnetic field, the planet is defenseless against stellar wind. With one, it has a fighting chance, but still faces atmospheric erosion over billions of years. That's why finding any atmosphere on this planet would be remarkable. The star has had billions of years to strip it away. The planet orbits close enough that escape velocity is low, making atmospheric loss easier. Every piece of physics says this world should be airless, yet the telescope detected water vapor. How? The only plausible answer involves volcanism. If the planet is still geologically active, volcanic eruptions could inject water vapor into the atmosphere faster than the star strips it away. On Earth, volcanoes release steam from underground reservoirs. On JJ486b, volcanoes might do the same thing, creating a temporary atmosphere that gets destroyed and replenished in an endless cycle. The atmosphere would exist in a steady state, constantly losing gas to space and constantly gaining gas from below. It would be fragile, thin, and unlike any atmosphere in our solar system. That brings us to the bizarre possibility this discovery represents. Picture a planet hemorrhaging steam from countless wounds. Volcanoes erupt across its surface, blasting superheated water vapor into a thin shell of air. The star's radiation immediately begins destroying that air, breaking water molecules apart and letting hydrogen escape to space. But before the atmosphere can vanish completely, another eruption replenishes it. The cycle continues, a brutal equilibrium between creation and destruction. This is the only way JJ486b could maintain a water vapor atmosphere despite 800-degree temperatures and relentless stellar radiation. Volcanic activity requires heat, and heat requires energy. Rocky planets start with primordial heat from their formation, when countless impacts and gravitational compression heated the interior to thousands of degrees. They also generate heat through radioactive decay. Elements like uranium, thorium, and potassium decay slowly over billions of years, releasing energy. A planet 3 times Earth's mass would have 3 times the radioactive material, generating 3 times the heat. That heat has to go somewhere. It flows outward through the rocky mantle, sometimes breaking through the surface as volcanism. Earth has roughly 50 to 70 active volcanoes erupting at any given time. These eruptions release water vapor, carbon dioxide, sulfur dioxide, and other gases. Over geological time, volcanic outgassing created Earth's atmosphere and oceans. The same process could work on JJ486b, but with a crucial difference. The atmosphere gets destroyed as fast as it forms. On Earth, our atmosphere built up over millions of years because nothing was removing it. On this exoplanet, stellar radiation removes it constantly, so volcanism would need to be far more intense to maintain even a thin atmosphere. Scientists can estimate how much volcanic activity would be needed by calculating atmospheric loss rates. The star's ultraviolet radiation and stellar wind carry away gas at a rate depending on the radiation intensity and the planet's gravity. Higher gravity helps retain atmosphere. Lower gravity makes retention harder. JJ486b's gravity is about 3 times Earth's, which helps, but the stellar radiation is far more intense than what Earth receives, which hurts. Balancing these factors suggests the planet would need volcanic activity, perhaps 10 or more times Earth's rate, to maintain a steady-state water vapor atmosphere. Is that plausible? Maybe. Io, Jupiter's moon, is the most volcanically active body in our solar system. It has hundreds of active volcanoes erupting continuously, driven by tidal heating from Jupiter's gravity. Io's surface is constantly being resurfaced by lava flows. If GJ 486b has similar levels of geological activity, driven by residual heat from formation plus radioactive decay, it could theoretically supply enough volcanic gas to balance atmospheric loss. But we have no way to confirm this without direct observations of the surface, which are impossible with current technology. The water itself would come from the planet's interior. When planets form from the disk of gas and dust around young stars, they incorporate water in several forms. Some gets trapped in mineral crystals. Some exists as ice in the cooler outer regions. Some dissolves in molten rock. When the planet heats up, this water can be released through volcanic eruptions. Earth's mantle contains vast amounts of water, more than exists in all our oceans combined. GJ 486b's interior could harbor similar reservoirs, feeding volcanic steam production for billions of years. But here's the sobering part. Even if volcanism is supplying water vapor, that doesn't mean the planet has a stable atmosphere like Earth's. It would be more like a thin veil of steam constantly being replenished and destroyed. The atmospheric pressure might be a fraction of Earth's. The air might only extend a few miles above the surface before thinning to nothing. Standing on that surface, if you could survive the heat, you'd barely notice the atmosphere at all, just a shimmering haze above the scorched rocks. Whether this volcanic steam factory scenario is real depends entirely on whether the water vapor is actually on the planet, and that's still an open question. If the water vapor truly wraps around GJ 486b, it would create something our solar system has never seen, an atmosphere made entirely of steam, no nitrogen, no oxygen, no carbon dioxide. Just water vapor, surrounding a rocky planet at 800 degrees. Earth's atmosphere is 78% nitrogen and 21% oxygen, with water vapor making up only about 1% on average. Mars has carbon dioxide. Venus has carbon dioxide with sulfuric acid clouds. The gas giants have hydrogen and helium with traces of methane and ammonia. But pure water vapor? That exists nowhere in our planetary family. Kevin Stevenson from Johns Hopkins University put it simply: there is no comparable atmosphere in our own solar system. This statement carries weight because it means scientists have no reference point. They can't look at another planet and say, it should behave like that one. They have to build entirely new models from scratch, combining physics and chemistry in ways never tested before. The temperature would affect how water molecules interact. The pressure would determine how thick the atmosphere could be. The stellar radiation would control how long it could last. Water vapor behaves differently at different temperatures and pressures. On Earth, water exists in all three phases: solid ice, liquid water, and gaseous vapor. The transitions between these phases happen at specific temperatures and pressures. But GJ 486b's surface is far too hot for liquid water or ice. Everything would be vapor. That vapor would interact with the rocky surface in strange ways. Hot water vapor can chemically react with minerals, slowly breaking down rocks over geological time. On Earth, this process happens in volcanic fumaroles and hot springs. On this planet, it could happen across the entire dayside. The atmospheric chemistry would be bizarre. Water vapor molecules would be constantly bombarded by ultraviolet light from the star, splitting them into hydrogen and oxygen. The hydrogen would escape to space. The oxygen would either escape more slowly or react with the surface rocks, oxidizing iron and other metals. This creates a chemical imbalance where the atmosphere is continuously losing hydrogen faster than oxygen. To maintain the atmosphere, volcanic eruptions would need to supply water vapor with the correct hydrogen to oxygen ratio faster than the imbalance develops. Temperature gradients would drive intense weather patterns if enough atmosphere exists. The day side, heated to 800 degrees, would have rising columns of superheated steam. The night side, potentially hundreds of degrees cooler, would have descending flows of condensing vapor. Between them, winds would roar at supersonic speeds, possibly exceeding 1,000 miles per hour. These winds would carry heat from day to night, preventing either side from reaching its maximum extreme temperature. But they would also create turbulence, storm systems, and atmospheric dynamics unlike anything meteorologists have studied. The atmosphere's thickness remains unknown. It could be dense enough to create significant surface pressure, similar to Venus, or it could be whisper-thin, barely enough to detect. The transmission spectroscopy observations can't distinguish between these scenarios. They only detect the presence of water vapor, not the total amount. Future observations might reveal more by measuring how much the atmosphere affects the planet's temperature distribution. But before scientists can study this alien atmosphere's properties, they need to prove it exists at all, and that requires understanding how the telescope isolated such a faint signal. Stars are blinding. That's the fundamental problem with studying exoplanets. A typical star outshines its planets by factors of billions. Trying to see a planet next to its star is like trying to see a firefly next to a searchlight. The glare overwhelms everything. For decades, this glare limitation meant scientists could only find planets indirectly by measuring how they affect their stars. They couldn't actually see the planets themselves. Then engineers invented coronagraphs, devices that block starlight while letting planetary light through. The concept sounds simple, but the execution is extraordinarily difficult. A coronagraph uses precisely shaped masks or carefully angled mirrors to cancel out light from the star while preserving light from nearby objects. The James Webb Space Telescope carries several coronagraph designs, each optimized for different situations. For observing transits like JJ486b, the telescope doesn't use a coronagraph because the planet passes directly in front of the star. But for other exoplanet observations, coronagraphs are essential. The masks themselves are engineering marvels. They're shaped like complex patterns of concentric circles or spirals, designed using mathematical principles that dictate how light diffracts and interferes. When starlight hits the mask, the shape causes different light waves to cancel each other through destructive interference. The star's light diminishes by factors of thousands or millions. Meanwhile, light from a planet slightly off to the side doesn't hit the mask in the same way, so it passes through with minimal reduction. But there's a catch. Coronagraphs only work if the optics are nearly perfect. Any tiny imperfection in the telescope's mirrors, any slight vibration or thermal expansion, creates artifacts that can look like planets. Engineers spend years testing and calibrating coronagraphs to distinguish real signals from false ones. They observe known stars without planets to create reference images showing what pure artifacts look like. They observe stars with known planets to verify the coronagraph is working correctly. Only after extensive validation can they trust new observations. The Webb telescope's coronagraphs operate in infrared light, wavelengths invisible to human eyes, but perfect for studying cool objects like planets. Rocky planets emit most of their light in infrared because of their surface temperature. Gas giants also glow in infrared from residual heat left over from their formation. By observing in infrared rather than visible light, the telescope increases the planet to star brightness ratio. The star is still far brighter, but the difference shrinks from billions to millions or thousands. That improvement makes all the difference. For JJ486b specifically, the telescope didn't need to spatially separate the planet from the star because the planet transits. During transit, the planet's silhouette blocks a tiny fraction of starlight. The telescope measures that dip in brightness and analyzes the spectrum of light filtering through the planet's potential atmosphere. No coronagraph needed for this geometry. but coronagraphs remain crucial for direct imaging of planets that don't transit, including future attempts to photograph Earth-like worlds orbiting Sun-like stars. The next challenge involves choosing the right instrument for the job. Two instruments on the James Webb Space Telescope can study planetary atmospheres, but they operate differently and provide complementary information. NIRSpec, the near-infrared spectrograph, observed GJ 486b and detected the water vapor signal. NIRIS, the near-infrared imager and slitless spectrograph, could potentially solve the mystery of whether that water comes from the planet or the star. Understanding why requires understanding how each instrument works and what wavelengths they observe. NIRSpec covers wavelengths from about 0.6 microns to 5.3 microns, prime territory for detecting molecular absorption features. Water vapor absorbs strongly around 1.4 microns, and again around 2.7 microns. Carbon dioxide absorbs near 4.3 microns. Methane has features around 2.3 and 3.3 microns. NIRSpec can spread these wavelengths into detailed spectra, showing precisely which molecules exist and in what concentrations. The instrument used high-resolution mode for the GJ 486b observations, providing excellent spectral detail. But NIRSpec has a limitation. At the shortest wavelengths it observes, around 0.6 to 1.0 microns, the instrument's sensitivity drops. This is exactly the wavelength range where planetary atmospheres and stellar starspots produce different signals. Computer models show that below 1 micron, water vapor in a hot planetary atmosphere creates one type of spectral feature, while water vapor in cool starspots creates a different feature. NIRSpec can barely see these wavelengths, making it impossible to distinguish the two scenarios. NIRIS fills this gap. It operates at slightly shorter wavelengths, from 0.6 microns up to about 2.8 microns, with excellent sensitivity below 1 micron. More importantly, NIRIS uses a technique called single-object slitless spectroscopy that's particularly good for bright targets like red dwarf stars. The instrument can observe an entire transit from start to finish, creating time-resolved spectra that show how the signal changes as the planet moves across the star's face. If the water vapor comes from the planet's atmosphere, the signal should remain constant throughout the transit. The planet carries its atmosphere with it, so the absorption features don't change. But if the water vapor comes from star spots, the signal might vary during transit as the planet crosses spots of different temperatures and sizes. The spot distribution across the star's surface is uneven. Some regions have many spots, others have few. As the planet traverses the stellar disk, it samples different regions, potentially creating a time-variable water vapor signature. NIRIS can also measure the spectrum at the shorter wavelengths where the two scenarios diverge. Theoretical models predict that planetary water vapor produces a rising spectrum towards shorter wavelengths, while starspot water vapor produces a falling spectrum. The difference comes from temperature effects. Planetary atmospheres at 800 degrees behave differently than stellar photospheres at 6,000 degrees, with embedded 4,000-degree spots. NIRIS should be able to see this divergence and definitively answer whether the water is planetary or stellar. The catch is that NIRIS observations haven't been completed yet. The research team proposed them, but getting telescope time is competitive. Hundreds of proposals compete for limited observing hours. Some proposals get accepted immediately, others wait years. The GJ 486b NIRIS observations were approved, but the exact timing remains uncertain. Until those observations happen and data gets analyzed, the mystery persists. Meanwhile, other observations have already complicated the story. August 24th, 2024. A new scientific paper dropped like a bomb on the GJ 486b debate. The title was blunt. No, thick atmosphere on the terrestrial exoplanet. Good luck. JWST-486b. The paper presented results from 2 additional telescope observations using a different technique called secondary eclipse spectroscopy. Instead of watching the planet transit in front of the star, the observations measured what happened when the planet passed behind the star. The conclusion challenged everything the earlier transmission spectroscopy suggested. Secondary eclipses reveal different information than transits. When the planet goes behind the star, the system's total brightness drops slightly because we lose the planet's thermal emission. By measuring how much the brightness drops at different wavelengths, scientists can determine the planet's dayside temperature and look for emission features from the atmosphere. If a thick atmosphere exists, it should transport heat and show spectral features from molecules glowing at infrared wavelengths. The new observations showed neither. The team measured the planet's dayside temperature at 865 degrees Fahrenheit, give or take 14 degrees. That precision is remarkable, but more important is watching the day side and warming the night side. That transport would lower the dayside temperature significantly below the maximum. But JJ-486b's dayside temperature is almost exactly what you'd expect for bare rock. The paper concluded that the planet either has no atmosphere or possibly a very thin one with less than 1% water vapor or less than 1 part per million carbon dioxide. This result directly contradicts the water vapor detection from transmission spectroscopy. How can both be true? The answer might lie in the different techniques' sensitivities. Transmission spectroscopy looks at starlight filtering through the very top of the atmosphere, the highest, thinnest layers. Secondary eclipse spectroscopy looks at thermal emission from the entire day side, sampling deeper layers. It's possible the planet has a very thin, high-altitude layer of water vapor that transmission spectroscopy detected, but not enough atmosphere to significantly affect heat transport. Alternatively, the transmission spectroscopy might have detected stellar water vapor in star spots rather than planetary water vapor. The secondary eclipse observations support this interpretation because they show no evidence for atmospheric heat transport. If the planet were wrapped in a water vapor atmosphere thick enough to produce the transmission spectroscopy signal, that atmosphere should also transport heat. The fact that it apparently doesn't suggests the water vapor isn't there. The August 2024 paper represents the scientific process working as intended. One team reports a detection. Another team tests it with a different method. The results disagree. Now, scientists must figure out which result is correct, or whether both are correct, but measure different things. The debate continues, but the new data shifts the odds toward the star spot explanation. But what does no thick atmosphere really mean in this context? Airless doesn't mean vacuum. Even Mercury, the most obviously airless planet in our solar system, has a wispy exosphere of atoms kicked up from the surface by solar wind impacts. The Moon has a similar exosphere. These ultra-thin atmospheres have pressures millions of times lower than Earth's. You couldn't breathe them. You couldn't hear through them. For most purposes, they don't exist, but they're technically there, detectable by sensitive instruments. When scientists say JJ-486b might be airless, they mean something like this: an atmosphere so thin it barely matters. Atmospheric pressure on Earth at sea level is about 14.7 pounds per square inch. That pressure comes from the weight of all the air above you pressing down. Climb a mountain, and pressure decreases because there's less air above. Travel to space, and pressure drops to nearly zero. The boundary between atmosphere and space is fuzzy, but most definitions put it somewhere around 60 miles altitude. Above that height, the air is so thin that spacecraft don't experience significant drag. Venus, by contrast, has surface pressure 90 times Earth's. Standing on Venus, the air pressure would feel like being 3,000 feet underwater. The atmosphere would crush you long before the heat killed you. Mars falls between these extremes with surface pressure only about 0.6% of Earth's. Mars's air is too thin to breathe. but thick enough to create weather, dust storms, and clouds. These are all thick atmospheres, in the sense that they significantly affect their planet's climates and surfaces. GJ 486b might have something far thinner. Imagine atmospheric pressure, 1/10 of Mars, or 1/100th, or 1,000th. At some point, calling it an atmosphere becomes misleading. It's more like a thin haze of molecules, occasionally bouncing off the surface before escaping to space. Such an atmosphere wouldn't transport heat, it wouldn't create weather, it wouldn't protect the surface from radiation, it would barely interact with starlight passing through it. Yet it might still produce detectable spectral features if the molecules are concentrated at high altitude where transmission spectroscopy looks. The phrase, "no thick atmosphere," in the August 2024 paper is carefully chosen. It rules out Earth-like or Venus-like atmospheres, but leaves room for something ultra-thin. The paper's abstract states, the results are consistent with an airless body with a slight non-zero albedo, or a thin atmosphere with less than 1% water vapor. That, less than 1%, phrasing is crucial. Earth's atmosphere is 0.4% water vapor on average. Less than 1% could still mean the planet has significant water vapor by some definitions, just not enough to affect heat, transport, or produce strong secondary eclipse signals. Understanding these distinctions matters because the definition of atmosphere affects whether GJ 486b counts as a historic discovery or a false alarm. If the planet has even a wisp of genuine atmosphere, even something far thinner than Mars, it would still be the first rocky exoplanet with confirmed atmospheric gas. That milestone matters for understanding planetary formation and evolution. But if the planet is truly airless and the water vapor signal comes from star spots, then scientists are back to searching for the first rocky exoplanet atmosphere. The semantic debate reflects a deeper issue in exoplanet science. Red dwarf stars host a cosmic graveyard of dead atmospheres. Billions of rocky planets orbit these cool suns throughout the galaxy, and most of them probably started with air. Gas left over from planetary formation would have wrapped around newly formed worlds, creating primordial atmospheres of hydrogen, helium, water vapor, and other volatiles. Then the stars woke up. Young red dwarfs, particularly in their first billion years, unleash radiation storms that would make our sun's worst tantrums look gentle. Ultraviolet light, X-rays, stellar flares increasing brightness by factors of 10 or more. The radiation strips atmospheres away layer by layer, year by year, until only bare rock remains. This is the M-dwarf planet problem. M-dwarfs are the most common stars in the universe, making up roughly 70% of all stars. Rocky planets around M-dwarfs are even more common. Estimates suggest there could be billions of Earth-sized worlds orbiting in the habitable zones of red dwarf stars in our galaxy alone. But if these planets can't keep their atmospheres, they can't support life. The potential for inhabited worlds across the galaxy plummets. Billions of planets become billions of sterile rocks. Scientists debated this problem for decades before the James Webb Space Telescope launched. Some argued that rocky planets around M-dwarfs would be airless without exception. The radiation is too intense. The planets orbit too close. Atmospheric escape is inevitable. Others argued that planets might hold on through various mechanisms: strong magnetic fields deflecting stellar wind, high planetary mass creating stronger gravity, continuous volcanic outgassing, replenishing lost atmosphere faster than radiation removes it. The debate remained theoretical because no one could definitively detect or rule out atmospheres on rocky exoplanets around red dwarfs. GJ 486b was supposed to help settle this debate. The planet is large enough that its gravity helps retain atmosphere. It orbits a red dwarf that's billions of years old, past its most violent youth. If any rocky planet around a red dwarf could keep an atmosphere, this one seemed like a good candidate. The initial water vapor detection sparked hope. Maybe atmospheres can survive after all. Maybe billions of worlds remain habitable. But the August 2024 paper showing no thick atmosphere revived pessimism. Maybe atmospheres can't survive. Maybe the red dwarf graveyard is real. The implications extend beyond habitability. Atmospheric survival affects how scientists search for life. Most biosignature searches focus on atmospheric gases that life produces, like oxygen or methane. In combination, if rocky planets around red dwarfs can't maintain atmospheres, scientists should focus their life-hunting efforts on planets around sun-like stars instead. But sun-like stars are rarer than red dwarfs. The number of searchable worlds drops dramatically. The timeline for finding life stretches from decades to centuries. There's also a mass threshold to consider. Larger rocky planets have stronger gravity, making atmospheric retention easier. GJ 486b, at 3 times Earth's mass, represents the high end of rocky planet sizes. If even this massive world struggles to keep an atmosphere, smaller Earth-sized planets have no chance. Conversely, if GJ 486b does have an atmosphere, despite all challenges, it suggests smaller planets might also succeed under the right conditions. The answer determines which planets are worth studying and which can be ignored. The question remains agonizingly unresolved. Some observations suggest water vapor, others suggest no thick atmosphere. Until someone definitively proves or disproves atmospheric gas on this or similar planets, the M-dwarf planet problem remains open. But there's another planet we can compare this to. Venus and GJ 486b are twins separated by cosmic distance. Both are rocky planets. Both have surface temperatures around 800 degrees Fahrenheit. Both orbit closer to their stars than Earth does. But Venus has a crushing atmosphere of carbon dioxide, while GJ 486b might have no atmosphere at all. Understanding why these similar worlds follow different paths could reveal fundamental truths about planetary evolution. Venus's atmosphere weighs 90 times Earth's entire atmosphere. The surface pressure is crushing, equivalent to being 3,000 feet underwater. The atmosphere is 96% carbon dioxide, with clouds of sulfuric acid floating 30 miles above the surface. Those clouds reflect most sunlight back to space, giving Venus a high albedo. But enough light penetrates to heat the surface, and the thick carbon dioxide atmosphere traps that heat through the greenhouse effect. The result is a runaway greenhouse that maintains hellish temperatures day and night. How did Venus get this way? The planet probably started with liquid water oceans similar to early Earth, but Venus orbits closer to the Sun, receiving almost twice as much sunlight as Earth. That extra energy caused more ocean water to evaporate into water vapor. Water vapor is a greenhouse gas, so it trapped heat, warming the planet further and evaporating more oceans. The cycle accelerated until all the water was in the atmosphere. Ultraviolet light from the sun split the water molecules apart. Hydrogen escaped to space. Oxygen reacted with surface rocks. The water was gone, replaced by volcanic carbon dioxide that had no oceans to dissolve into. The carbon dioxide accumulated, creating the thick atmosphere Venus has now. GJ 486b could have followed a similar path initially. The planet might have started with water oceans. The close orbit and intense stellar heating would have evaporated those oceans quickly. Water vapor accumulated in the atmosphere. Then the red dwarf's ultraviolet radiation split the water apart even faster than our sun did on Venus. Hydrogen escaped, oxygen escaped, or reacted with rocks. The water vanished within perhaps a few 100 million years. Unlike Venus, which then accumulated carbon dioxide, GJ 486b might not have had substantial volcanic outgassing of carbon dioxide. Or if it did, the stellar wind stripped that gas away too. The end result, an airless world. But here's where the comparison gets interesting. Venus has such a thick atmosphere, partly because it's far enough from the Sun that stellar wind doesn't strip it away efficiently. Venus also might lack a strong magnetic field, but the thick atmosphere itself provides protection. The upper atmosphere absorbs ultraviolet light and stellar wind particles, shielding the lower atmosphere. JJ 486 b orbits much closer to its star, where stellar wind is more intense. Even if the planet tried to build a thick atmosphere through volcanic outgassing, the stellar wind might remove gas faster than volcanism supplies it. Temperature also differs in a crucial way. Venus's surface is hot because of the greenhouse effect, not because of proximity to the Sunday. Without its thick atmosphere, Venus would be much cooler. JJ 486b's surface is hot because of stellar proximity. Remove any thin atmosphere the planet might have, and the temperature barely changes. This tells us something important. JJ 486b's heat comes from external radiation, not internal atmospheric insulation. Venus trapped its own heat. This planet can't. The comparison highlights how small differences in orbital distance, stellar type, and planetary properties can lead to wildly different outcomes. Venus ended up with too much atmosphere. JJ 486b ended up with too little or none at all. Both are hellish, but in different ways. Understanding these differences matters for the next question. Would finding any atmosphere here count as a first? Scientists have found atmospheres on hundreds of exoplanets. Gas giants like Jupiter show clear spectral features. Hot Jupiters, gas giants orbiting close to their stars, have atmospheres studied in remarkable detail. Researchers have detected water vapor, methane, carbon monoxide, even atomic metals in these worlds' atmospheres. The techniques work beautifully for large planets with thick atmospheres, but rocky planets are different. Smaller, thinner atmospheres, if any exist at all, harder signals to detect. Until JJ 486b, no one had definitively found atmospheric gas around a rocky exoplanet outside our solar system. The discovery would shatter a barrier that stood for decades. Since the first exoplanet confirmation in 1995, thousands of planets have been found, thousands of gas giants characterized, thousands of hot Jupiters studied, but zero rocky planets with confirmed atmospheres, zero Earth-like or Venus-like worlds with detectable air. The technical challenge is immense. Rocky planets are small, typically 1 to 3 times Earth's size. Their atmospheres, if they exist, are thin compared to gas giants. The spectral features are subtle, easily overwhelmed by noise or confused with stellar contamination. Finding the first rocky exoplanet atmosphere would prove that the techniques work. It would validate decades of instrument development and analysis methods. It would show that transmission spectroscopy, secondary eclipse observations, and other methods can achieve the sensitivity needed for small planets. That validation would justify building even more powerful future telescopes specifically designed to study rocky planet atmospheres. Billions of dollars in funding would flow toward characterizing Earth-like worlds. The search for habitable planets would accelerate dramatically. But the flip side matters too. If JJ 486b turns out to be airless, it suggests rocky planet atmospheres are even harder to detect than pessimists feared. It might mean current technology isn't quite good enough yet. Future telescopes would need even better sensitivity, larger mirrors, more sophisticated instruments. The timeline for characterizing Earth-like planets would stretch from years to decades. Finding life on other worlds would become a goal for future generations rather than the current one. The historic significance depends entirely on the ambiguous data. If transmission spectroscopy detected real planetary water vapor and the secondary eclipse observations simply missed a thin atmosphere, JJ 486b enters the history books. If transmission spectroscopy detected stellar water vapor from star spots and the secondary eclipse observations correctly showed no planetary atmosphere, the search continues. The difference between first detected atmosphere and another false alarm hinges on observations that haven't been completed yet. Scientists are careful not to claim victory prematurely. Sarah Moran's statement summarizes the situation perfectly. We see a signal, and it's almost certainly due to water. But we can't tell yet if that water is part of the planet's atmosphere. That uncertainty is honest and appropriate. Making premature claims that later get overturned damages scientific credibility. Better to wait for definitive proof than rush to judgment. The wait continues. Additional observations are planned. New analysis methods are being developed. Other rocky exoplanets around other red dwarfs are being studied with similar techniques. One way or another, the question will be answered. Either GJ 486b has an atmosphere or it doesn't. Either it's the first or the search continues. Either way, the answer matters, because the implications extend far beyond one planet, 26 light-years away. If GJ 486b can maintain any atmosphere at all, despite 800-degree temperatures and intense stellar radiation, it suggests something profound about cooler worlds. The planet orbits well inside the habitable zone, the region where liquid water could exist on a planet's surface. It's scorched, blasted by radiation, tidally locked with one side baking and the other freezing. Every factor works against atmospheric survival, yet transmission spectroscopy detected water vapor. Even if that atmosphere is thin, even if it's constantly replenished by volcanoes and stripped by stellar wind, its mere existence proves rocky planets can hold onto air in hostile environments. Now imagine a similar planet orbiting farther from its red dwarf star. Cooler surface temperatures, less intense radiation, more time for water vapor to persist before breaking down. Such a planet might maintain a stable atmosphere without needing constant volcanic replenishment. It could have oceans, clouds, weather, a water cycle, the ingredients for life. If the most extreme case, GJ 486b, manages to keep an atmosphere, then these calmer worlds almost certainly can too. The billions of rocky planets orbiting in red dwarf habitable zones across the galaxy remain viable targets for finding life. But if GJ 486b is truly airless, the implications flip. If even this large, massive planet with strong gravity can't hold on to atmospheric gas, what chance do smaller Earth-sized worlds have? The answer might be none. Rocky planets around red dwarfs might universally lose their atmospheres during the star's violent youth. The billions of potentially habitable worlds might all be sterile rocks. The search for life would need to focus exclusively on planets around sun-like stars, which are rarer and harder to study because they're dimmer and farther apart. There's a middle scenario too. Maybe only large rocky planets like GJ 486b can maintain atmospheres around red dwarfs. Maybe 3 times Earth's mass is the minimum threshold. That would still leave millions of super-Earths in habitable zones potentially able to support life. The galaxy wouldn't be as full of inhabited worlds as optimistic estimates suggest, but it wouldn't be empty either. Finding life would be harder, but not impossible. The habitable zone itself might need redefining based on what GJ 486b teaches us. Traditional definitions focus on distance from the star, where liquid water can exist on the surface. But if planets close to red dwarfs can't maintain atmospheres, then the inner edge of the habitable zone isn't determined by temperature alone. It's determined by atmospheric survival. Planets might be cool enough for liquid water, but airless, making them uninhabitable, despite being in the habitable zone. The true habitable zone might be narrower than we thought. Another implication involves how life adapts. Even if GJ 486b has a thin atmosphere constantly stripped and replenished, that dynamic environment might preclude life. Life needs stability. It needs consistent conditions over millions of years for evolution to work. A planet with an atmosphere that exists in steady-state equilibrium between creation and destruction might be too unstable for biology to take hold, or maybe life could adapt to such conditions. Earth has extremophile organisms living in volcanic vents, acidic hot springs, and deep ocean trenches. Maybe exo-extremophiles could survive on planets with transient atmospheres. The question ultimately comes down to what we find on GJ 486b and similar worlds. Each rocky planet studied adds data points to our understanding. Each atmosphere detected or ruled out narrows the possibilities. Eventually, patterns will emerge. Scientists will know which types of planets can keep air and which can't. They'll know where to focus life-hunting efforts and where to avoid wasting time. But first, we need to address a common misconception about this discovery. Finding water vapor does not mean finding light of gases that life produces and that can't easily be explained by geology or atmospheric chemistry alone. On Earth, oxygen is a biosignature. Our atmosphere is 21% oxygen because photosynthetic organisms produce it continuously. Without life, geological processes would remove oxygen from Earth's atmosphere within a few million years through reactions with rocks and volcanic gases. The presence of so much oxygen suggests biology, but even oxygen alone isn't conclusive. Planets can produce oxygen through non-biological processes, like water vapor being split by ultraviolet light. The strongest biosignatures are combinations: oxygen plus methane, methane plus nitrous oxide. These combinations are chemically unstable. They shouldn't coexist in the same atmosphere without constant replenishment. Life can produce both simultaneously. Geology struggles to produce both together. Finding such combinations would be strong evidence for biology, though not absolute proof. Scientists talk about confidence levels. One gas might be 10% confidence. Two contradictory gases together might be 90% confidence. You never reach 100% without directly observing organisms. GJ 486b's water vapor, even if confirmed to be planetary, has 0% biosignature value. Water vapor is completely explainable through volcanic outgassing. It requires no life. It provides no evidence for life. It doesn't even suggest the planet could support life, because the surface temperature is 800 degrees. If life exists on this world, which seems impossibly unlikely, the water vapor detection tells us nothing about that life. The water is geologically interesting, atmospherically interesting, but biologically irrelevant. This matters because media coverage of exoplanet discoveries often sensationalizes findings. Headlines scream, "Water found on alien world," with implications of imminent alien contact. The reality is far more mundane. Scientists found hints of water vapor that might be from a planet or might be from star spots on the host star. Even if it's from the planet, it just means volcanoes might be erupting, nothing more. Setting appropriate expectations prevents public disappointment and maintains trust in science. There's also the issue of false positives. Throughout the history of exoplanet science, researchers have announced potential biosignature detections that later turned out to be instrumental errors, stellar contamination, or misinterpreted data. Each false alarm makes the public more skeptical of real discoveries when they eventually happen. The boy who cried wolf effect applies to science too. Overclaiming biosignatures damages the field's credibility. Better to be conservative and clear about what's been found versus what hasn't. GJ 486b teaches scientists how to study rocky exoplanet atmospheres, assuming it has one. The lessons learned apply to future observations of more Earth-like worlds in habitable zones where biosignatures might actually exist. Consider it practice, a test case, a dry run for the real thing. When the James Webb Space Telescope or future instruments eventually study a truly habitable world, the techniques refined on GJ 486b will be ready. Scientists will know how to separate planetary signals from stellar contamination. They'll know which wavelengths to observe and which analysis methods work best. That brings us to the final question. What happens next? The story of GJ 486b is unfinished. Additional observations with the telescope's NIRISS instrument could definitively determine whether the water vapor comes from the planet or the star. Those observations remain scheduled but not yet executed. When they happen, probably within the next year or two, scientists will analyze the data and publish results. If NIRISS shows the water is stellar, the case closes. The planet is likely airless, and the search for the first rocky exoplanet atmosphere continues. If NIRISS confirms the water is planetary, even a thin atmosphere counts as historic. Beyond GJ 486b, dozens of similar planets await study. Scientists have identified hundreds of rocky exoplanets around red dwarf stars, close enough for detailed atmospheric characterization. Some are even more favorable targets than GJ 486b because their stars are less active or their orbits are better aligned. The telescope can only observe a small fraction of these worlds during its mission lifetime, which raises difficult choices about which planets to prioritize. Every hour spent on one target is an hour not spent on another. The Nancy Grace Roman Space Telescope, scheduled to launch in 2026 or 2027, will join the search. Roman will have different capabilities than Webb, including the ability to directly image some planets, rather than relying only on transits. Together, the two telescopes will provide complementary data on rocky exoplanet atmospheres. Roman might catch things Webb misses, and vice versa. The combination increases the chances of finally detecting the first confirmed atmosphere on a rocky world. Ground-based telescopes are improving too. The extremely large telescope in Chile, under construction now, will have a primary mirror 39 meters across when completed in the 2020s. That huge mirror will collect more light than any previous telescope, potentially enabling atmospheric studies of rocky planets around nearby stars. The telescope will work differently than space-based observatories because Earth's atmosphere interferes with observations, but sophisticated adaptive optics systems can compensate for atmospheric turbulence. The combination of space and ground-based observations will accelerate progress. Longer term, proposals exist for even more ambitious missions. Telescopes specifically designed to study Earth-like planets. Missions carrying dozens of instruments optimized for biosignature detection. Projects that would take decades to develop and cost billions of dollars. Whether these missions get funded depends partly on what current observations reveal. If the James Webb Space Telescope confirms atmospheres on multiple rocky exoplanets, funding agencies will be more likely to support future missions. If rocky exoplanet atmospheres prove too difficult to detect, funding might shift elsewhere. The ultimate goal is finding life. Every step toward characterizing rocky exoplanet atmospheres moves closer to that goal. GJ 486b might not have life and might not even have an atmosphere, but studying it develops the techniques needed to eventually find habitable worlds. Each observation teaches something. Each ambiguous result points toward better methods for future work. Science progresses incrementally through exactly this kind of painstaking investigation. Within a few years, maybe sooner, scientists will know definitively whether GJ 486b has an atmosphere. They'll know if rocky planets around red dwarfs can survive atmospheric stripping. They'll know where to focus future searches for habitable worlds. The answers will reshape our understanding of how common life might be in the universe. They'll determine whether humanity is likely to find neighbors or whether we're isolated in a galaxy full of sterile rocks, 26 light-years away, a planet either wrapped in steam or bare, as the moon orbits its red dwarf star. In laboratories and universities across Earth, scientists wait for telescope time, analyze data, and debate interpretations. The mystery persists, the ambiguity frustrates, but the search continues. Because somewhere in the cosmos, perhaps on a planet much like GJ 486b, but farther from its star and cooler, life might exist. Finding it starts with understanding worlds like this one, learning which planets can keep air and which cannot, building the knowledge and tools to eventually answer humanity's oldest question: are we alone? The answer, whatever it is waiting in the light filtering through distant atmospheres,